So this is the video to go over how to write Lewis structures using VSEPR theory, coming up with the hybridization of the bonds, and determining whether or not the molecule is polar. So we're going to kind of put all that together. And what I've done, I gave you a worksheet to work on. These molecules may not match what's on the worksheet in terms of the exact molecules, but what I tried to do was find an example of each type of molecule that you might encounter, a couple of things that you might have to look out for in terms of the polarity, the exceptions to the octet rule, and what to do when you have a polyatomic ion. So I tried to cover everything in here. These molecules, some of them may be the same, some may be different, but they're the same types of things you might encounter. So the first molecule, silicon tetrafluoride. So if we lay out our molecule, we've got silicon, which is going to be in the middle because there's one silicon, there's 4 fluorides. And if we do our NaSl, then we have 5 total atoms here, 4 fluorines and a silicon. None of them are hydrogen, which means the total number of needed electrons would be 40, 5 times 8. It's always 8 times the number of atoms unless you have a hydrogen, and then any hydrogens only count for 2 in the N category. So now we're going to figure out how many electrons we actually have available. Well, each of the fluorines, because that's from group 17, they're each going to have 7. So 7 times 4 is 28. The silicon is going to have 4. That gives us a total of 32 available electrons that we can use. And the difference between what we need and what we have available is 8. 8 electrons can form 4 bonds. It takes 2 to make a bond. So if I draw 1, 2, 3, 4 bonds, then that takes care of the 8 shared electrons, which means what I have left to make lone pairs with are 24 leftover electrons for lone pairs. And if I distribute them evenly, that's 6 on each of the fluorines. And when you go back around and look at all of the atoms, they now all have 8 electrons. Right? The fluorines each have 6 dots, 6 lone pairs, or 6 lone pair or unbonded electrons, and then 1 bond. That makes a total of 8. Right, 2, 4, 6, 8, and that's the same for all 4 fluorines. And then the silicon has 1 bond, 2 bonds, 3 bonds, 4 bonds. There's your 8 around the silicon. So all the atoms have satisfied the octet rule, and we've taken care of all of the electrons that we started with, no more, no less. So that's the Lewis structure. The shape, again, when it comes to things like the shape and the hybridization, we are only looking at the central atom. So this central atom has a total of 4 domains or regions of density or regions of electrons around it. So 4 electron domains with no lone pairs. They're all bonding pairs. That is called tetrahedral in shape. The hybridization is always starts with sp, and then if you have 4 or fewer regions around the central atom, the exponent on the p is always sort of n-1. So with 4 bonds or 4 regions, it's going to be an sp3 hybridization. So we've got the Lewis structure, we've got the shape tetrahedral, we've got the sp3 hybridization. So the last question is whether this molecule is polar. Well, pretty much any time, and it doesn't really matter what the shape is here, the general rule is if you have the same atom on all sides of the central atom, this molecule is never going to be polar. We can assume most of the time, anytime you have 2 nonmetals like silicon and fluorine, or carbon and chlorine or anything like that, any combination of things that aren't metals, the bonds are going to be at least somewhat polar. So in this case, all these fluorines are going to hog the electrons. So each of the fluorines has that partial negative charge on it, which means the silicon has the partial positive charge. But because the negative charge goes all the way around evenly, this is a non-polar molecule. When it's the same on all sides, it's non-polar. Okay, BBr3. So boron is going to go in the middle, and then we have 3 bromines to bond to. Now this is going to be a case where we have an exception to the octet rule. Okay, and this is an unusual case because boron is one of only a couple of elements in the periodic table that will be satisfied, and that doesn't mean complete, but satisfied with 6 electrons. So that's going to be what's called the incomplete octet. It can be fairly stable with only 6 valence electrons connected to it, which means when you have boron as the central atom, you need to adjust the value used for N. So instead of having 4 times 8, you're going to have 3 times 8 for the 3 bromides, and then plus 6 for the boron. So this is, other than hydrogen, this boron is an exception to the octet rule where it only needs 6. So if we have 3 times 8 is 24 plus 6 is 30 electrons needed. The only other time where you might have this would be with aluminum, which can also get by with 6, but just to keep it simple, the only exception that I would put on the quiz part of this would be boron. So if you have boron as the central atom, use 6 for the need. And you're going to see how that plays out here in a second. So we have 30 electrons needed. We have available, bromine has 7, so that's 21, 7 times 3, and then boron has 3, so 21 plus 3 is 24, which means we only need to share 6 electrons, which is how we're going to end up with 3 bonds, 1 to each of the bromines, and then we're going to have a total of 18 electrons left over. So that means we're going to have 1, 2, 3, 4, 5, 6 electrons unbonded around each bromine, and that will give us the bromines each with 8 electrons connected. The boron has the 6 that it is happy with, so that gives us the complete Lewis structure. So again, the exception here is that boron will only need 6 electrons, which means 3 bonds. Now moving on to the shape, we have a central atom with 3 electron regions. A lot of times these electron regions, when it's not boron, but sometimes carbon can do this, sulfur, other atoms can do this as well, where you might have one of these be a double bond, and then that would still only count as 3 electron regions. But in this case, it's just 3 bonds, 3 electron domains or areas of density, no lone pairs. That shape is called trigonal planar. It is a flat triangle. And again, we're looking at the hybridization next. SP, and the exponent is the number of bonds minus 1. So since we have 3 bonds, or 3 electron domains, it's going to be an sp2 hybridization. And the last question is whether or not this is a polar molecule. Well, since we have, in this case, 3 corners or 3 sides essentially, and each of those 3 sides is the same, that means that this is a non-polar molecule, even though each of these bonds would be considered polar. But they're all polar with the same charge on all 3 sides. So there's no polarity because there's no positive pole. Okay, here's another one, NF3. Now nitrogen, unlike boron, is not satisfied with 6 electrons, so we're going to do our NaSl, just like we would with any of the other elements. We've got a total of 4 atoms. 4 times 8 is 32. Each of the fluorines contributes 7 valence electrons. Nitrogen contributes 5. So that's 26 total valence electrons, which means the difference between 32 and 26 is 6. So we're going to have to share 6 electrons and make 3 bonds. And then we have 20 electrons left over. So unlike in the boron molecule, this time when we put our 6 unbonded electrons around each of the fluorines, that only gets us 18 lone pair or unbonded electrons. According to the NaSl, we need 20, and nitrogen in the center only has 6 electrons in the 3 bonds, so that gives us space to put those 2 last electrons on the nitrogen atom. Now the nitrogen has 8 electrons around it, each of the fluorines has 8 electrons around it, and the Lewis structure is complete. So again, the only exception is that boron, where you can just be okay with just the 3 bonds and no lone pairs, and you only need 6 electrons for that. So the shape here, we have 4 electron domains or regions. 3 of them are bonding pairs. 1 is a unbonded pair or lone pair, and that is called trigonal pyramidal. So it's a pyramid with no atom in the center. Okay, the tetrahedral is a pyramid, but the center of the pyramid is actually an atom. In this case, what it would really kind of look like, if I could draw it in 3 dimensions, is one of the fluorines would be out toward us, one of the fluorines would be kind of over in the back, and then the nitrogen is at the top. So the triangle would be the 3 fluorines, and then the top of the pyramid is the nitrogen. In a tetrahedron, there's another atom that's in the center connected to all 4 of the corners. So we've got trigonal pyramidal. We have 1, 2, 3, 4 electron domains, which means the hybridization is sp3. So the hybridization is the same in tetrahedron and trigonal pyramidal, even though the shape's a little different. The shape is different because this unbonded pair of electrons pushes those bonds a little bit farther away than if this was a bond up to the top here, because the bonded electrons are not always around the nitrogen. They go back and forth, so they don't have as much influence as these unbonded electrons, which are always sitting in this space at the top. So those electrons, because they're more stationary, push those bonds down a little bit more than they would in a tetrahedron when there's 4 bonds. So that's the reason for the difference in the shape, even though the hybridization is the same. So the last question here is this a polar molecule? And the answer this time is that yes, this is polar, because we have, when you look at the shape down at the bottom that we drew here, okay, we've got the 3 fluorines essentially at the bottom, and we've got this nitrogen at the top. And so you have a difference from the bottom to the top. Okay, the 3 fluorines are going to have a different partial charge than the nitrogen. They're actually going to pull the electrons more away from the nitrogen in the bonds. So you're going to have, even though there's lone pair electrons up here, you're going to have more of a partial positive, you're going to have more of a partial negative on the bottom. So this is a polar molecule. Anytime you have different atoms sort of on one end or the other, that's when you're likely to have a polar situation. CS2. So we've got a carbon and 2 sulfurs. Let's put the carbon in the middle, because that's what usually happens. And since there's 2 sulfurs, they'll go on the other side. The N here, we've got 3 non-hydrogen atoms. So we're going to need 24 electrons. We have 2 sulfurs with 6 electrons each and a carbon with 4 electrons. That's a total of 16, 12 plus 4, which means we're going to need to share 8 electrons, and we're going to have 8 left over. So since we need to share 8 electrons and we only have 2 atoms to bond with, we're going to need 2 double bonds to share those 8 electrons. And then since we have 8 left over, each of the sulfurs gets 4 dots. Now, looking at the shape, we've got 2 bond regions, even though they're double bonds. Those double bonds connect the carbon. Each one of those double bonds connects the carbon to one other atom. So that only counts as 2 different domains. And 2 domains with no lone pairs is linear. Okay, so that's the shape. The hybridization here is sp, and since there's only 2 bonds, number of bonds minus 1 is 1. We don't need to write the 1 as a superscript because it's implied. We wouldn't put the p there if it wasn't p1, just like we wouldn't put the s there if it wasn't s1. So then we need to talk about polarity last. This has the same atoms on both ends of the line, which means even though these are likely to be slightly negative and this is likely to be slightly positive, the negative is on both ends. There's no south pole to go with the north pole or north pole to go to the south pole. So this is a non-polar. If you have a linear shape with the same type of atom on both ends, it's going to be nonpolar no matter what the polarity of the bonds might be. Because whatever it is on one side, it's going to be the same on the other, so you have no opposite pole. Okay, AsCl5. So this is going to be another one of our exceptions because we have 5 atoms to bond to and only 1 central atom to bond them with. So when we do our NaSl, so when we do our N, we have 6 total atoms. None of them is hydrogen, so that means we're going to need 48 electrons. Each of the chlorines has 7. The arsenic has 5. It's in the same family as nitrogen. So 7 times 5 is 35, plus 5 more for arsenic is 40, which according to the NaSl means we're going to need to share 8 electrons. Well, that makes 1, 2, 3, 4 bonds. Since we have to have another bond in order to bond to that 5th chlorine, we're going to change this from 8 to 10, and that will allow us to make that 5th bond, which means the lone pairs are going to be 30, and that happens to give us exactly enough to give 6 unbonded electrons to each chlorine. 6 times 5 is 30. And that gives each chlorine the 8 electrons that it wants. Arsenic has an expanded octet of 10 electrons, which means when we go to look at the shape, we're now looking at 5 bond regions. 5 bond regions results in what is called the trigonal, put it down here because it's long, trigonal bipyramidal shape. If I can spell it, pyramidal shape. Okay, it's essentially 2 pyramids with a chlorine at the top and the bottom, and then the 3 other chlorines form a triangle around the arsenic, sort of at the equator of the molecule. So if you look at it, it looks like 2 pyramids stuck together at the base. And the hybridization here, now we have more than 4 bonds, which means giving it a hybridization of sp3 is not enough. And the way these atoms get those extra bonds, the 5th or 6th bonds in these cases, is by involving d orbitals. So once you get past 4 bonds, you need to start adding d to your hybridization. So it goes sp3, and then the next bond gets into the D, so we get sp3d, and this would be sort of d1, but we don't need to write the 1. So that's the hybridization here. The polarity, well, we got lots of corners with a trigonal bipyramidal shape, but all the corners of this molecule are chlorines, which means it's the same all the way around, and it is nonpolar. Sulfur hexafluoride. This is going to be another exception. Has to be, because we've got 6 fluorines to bond to. So we're going to have more bonds than we normally would. More than 4, we've got to have 6. So 7 times 8 is going to be 56 that we need. The number that we have is 7 for each fluorine, so 6 times 7, which is 42, plus 6 more, which gives us 48. Well, again, looking at the numbers, it looks like we can only share 8 electrons, which would only give us enough to make 4 bonds. Well, we can't have that. We need 12 electrons here to add those last 2 bonds. So the number that we're going to have left over is going to be 36, which again works out ultimately because it gives us enough unbonded or lone pair electrons to give each of those fluorines the 6 that they need to fill them up with 8 apiece. Okay, so the shape here, we have 6 electron regions or domains, all bonding regions, which gives us the octahedral shape. The hybridization here, because we have 6, okay, sp3 gets us the first 4, and then d2 gives us the last 2. Okay, so we're moving farther into the d orbitals here, and then the last thing is the polarity. Again, lots and lots and lots of corners, but they're all the same, so non-polar. Okay, a polyatomic ion, drawing the structure of a polyatomic ion is essentially the same process for drawing molecular structures. There are just 2 differences for the process. The first is that the charge tells us that there are more or less electrons than there normally would be for this group of atoms. Okay, since it's a -2, that means that we have 2 electrons extra from what we would expect if you just counted up the valence electrons of these atoms. So the need here is 40 because there's 5 atoms, none of them are hydrogen. The number I have available, well, normally it would be 5 times 6 because that's the number of valence electrons for 4 oxygens plus the sulfur. But because of the -2, I have 2 extra that came from somewhere else, came from other atoms, which means I have a total of 32 available. That means I need to share 8. 1, 2, 3, 4 bonds means 8 electrons, and then 24 are going to be shared, which gives us 6 around each oxygen, satisfying the octet rule. Okay, so if I didn't have those 2 extra electrons here, I would have a much harder time satisfying all the atoms because I'd have 30 to work with, which would suggest I need 10 shared electrons, and then the math starts to get a little fuzzy there. So the only other difference here is that with a polyatomic ion structure, put the whole big thing in brackets, put the charge next to it. That shows anyone looking at this that we are acknowledging that there are 2 extra electrons here. This is in fact a polyatomic ion. We did it on purpose. And it's not just a mistake or us messing with the numbers to make it work. So put the whole thing in brackets, put the charge on the outside. Hybridization, 4 bond domains. That means it's an sp3. Okay, so just like with a molecule, if there's 4 regions around the central atom, it's an sp3 hybridization, whether it's a polyatomic ion or a molecular compound. And again, the polarity, even though it's an ion, so the group of atoms overall has this charge that would attract it to a positive ion. The molecule itself is nonpolar because it's the same on all 4 sides, and it's tetrahedral. Right, 4 bond regions, no lone pairs is a tetrahedral shape, and it's non-polar. because it's the same on all four corners. All right, H2O, O in the middle, hydrogen, hydrogen, NaSl. We need here 2 for each hydrogen, which is 4 plus 8 gives us 12. What we have available is 8, 1 from each of the hydrogen plus 6 for the oxygen. Means we share 4. That gives us 2 bonds. We have 4 left over. Never, 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 never put lone pairs on hydrogen, which means they're going to go on the oxygen. Now, when you put those lone pairs on the oxygen, the lone pairs really, really don't want to be near each other. And they really, really don't want to be near the bonds either. So that pushes the bonds down from a linear shape into a bent shape. So anytime you have what looks like it would probably be a linear shape, because you've got 1 atom in the middle and 2 on the outside, if there are lone pairs on that central atom, that lone pair or those lone pairs bend the molecule from the straight line into a bent shape. The hybridization here, we have 1, 2, 3, 4 bond regions. Doesn't matter for the hybridization whether they're lone pairs or bonds. There's 4, which means the hybridization is sp3. So even with 2 bonds, those 2 lone pairs also occupy hybrid orbitals. So the hybridization here is sp3. Because it is bent, because we have 2 lone pairs up here and the polarity is drawing the molecules or the electrons from the hydrogens in a hydrogen bond, this is a polar molecule. Okay, last one, and I'm just putting this in here because it is one case, one example rather, of a polar linear molecule. Most of the time when you have a linear molecule, you probably have the same thing on both ends. But in this case, because of the structure, because of the 3 different elements, we don't have the same thing on both ends. Okay, so what we're going to end up with, for that reason and another reason that we'll see in a second, this is going to end up being a polar molecule. Just put that down right now. Okay, need. I've got 2 non-hydrogens, so they would need 16, plus a hydrogen, 18. Available. The hydrogen has 1, the carbon has 4, that's 5, the nitrogen has 5, that's 10, which means I'm going to need to share 8 electrons. I need 4 bonds. I can only ever put 1 bond with a hydrogen, which means if I've got to have 4 bonds and I've got to have 4 bonds, I need a triple bond on the other side. So single bond to the hydrogen, triple bond to the nitrogen, which means there's 2 electrons left over. Can't put them on the hydrogen, never, 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 never. In theory, I could put them on the carbon, except the carbon already has 4 bonds, which means it's already got 8 electrons connected to it. So the last place to check is the nitrogen. Well, the nitrogen has these 3 bonds, that's 6. Nitrogen wants 8, so I can put those last 2 electrons over there on the nitrogen. Now here's where the polarity comes in. Nitrogen is more polar than either carbon or hydrogen. Carbon's more polar than hydrogen. Nitrogen is more polar than carbon. So the entire sort of electron cloud is going to be distorted toward the nitrogen end. A, because it's the most electronegative atom in the molecule. Also, you've got these 3 bond regions on that end of the molecule, and you've got this lone pair on that end of the molecule. So that makes this end of the molecule negative, makes this end of the molecule positive, makes the whole thing polar. Even though, because there are 2 bond regions on the central atom, it is linear, it is still polar because the 2 ends are different. And they're different in such a way that the partial charge is going to be favoring one end with negative with more electrons than the other. Last thing on this, what is the hybridization? Well, even though this is a triple bond, it only counts as one region because it's between the carbon and the nitrogen. All those electrons are moving back and forth between the carbon and the nitrogen, so that counts as one region. The hydrogen bond, the bond to the hydrogen, even though it's only a single bond, counts exactly the same as the triple bond on the other side in terms of the hybridization. So this is an sp hybridization. sp. Okay, so sp is always the number of bonds minus 1, so s and then p gives us sp hybridization. Alright, so there you go. Those are all examples of the different kinds of things you're going to run into with hybridization, Lewis structure, the shapes that you need to know. The 6, there's linear, trigonal planar, tetrahedral, bent, trigonal bipyramidal, and octahedral. And then the hybridization is SP, SP2, SP3, SP3D, SP3D2. That's going from 2 regions up to 6, respectively. And then determining the polarity. If you have the same atom all the way around the the central atom, if it's the same atom on both sides, or all 3 sides, or all 4 sides, or all 5 or 6 sides, if they're all the same, it's going to be nonpolar. If you have different things on different sides of the shape, then it's likely to be polar. So there you go. That's what you're going to be looking at on Monday.